Okay, so these are actually really important theorems. The schedule that you're following this semester is exactly the same schedule that was followed by Colonel Hartley when she did it. I just thought it's not broken, so I'm not going to try to fix it. It's a rapid schedule. So that's like, sometimes I feel like I'm spending more time on something like, okay, we're just going to spend today on existence and uniqueness theorems. You can write down any kind of model you want. It doesn't mean that it's going to be meaningful. It doesn't mean that solutions are even going to exist. And so that's what we're going to cover today. So just because you write an equation down does not mean it has a solution. It doesn't mean the solution is unique. You can easily have 2 solutions, 3. That's bad. If you want, a model that predicts something or tells you something, then you don't want to maybe have more than one solution to it. And so, and it doesn't mean also that it's going to be non-negative. For a lot of the models that I work on, I need the solutions to be non-negative. So I'm going to throw in non-negativity too. I think that's the thing I see the most, is people making mistakes in models. So I review papers, and sometimes I see papers that have negative solutions in them. And I can actually look at the equations and say right away, there probably are going to be negative solutions. So I'm going to give you those checkability theorems. Here's an example. Simple looking equation, xy prime equals y. You guys did separation of variables last time, so you separate variables. Natural logs. Exponentiate both sides. So what I do when I make my notes is I'm like, throw everything up on the palette, throw everything on my screen first, and then I start like putting in the details. So if you feel like you don't need these details, you can ignore it. If you don't remember, that's fine. I don't, retention of things is hard. Good? All right. But here, up here, when I did this move, I assumed that x is not 0. So this is also my style in the pure math classes too. I do use a lot of arrows for my things. I put up my proof and then I start putting in the details. No professors ever said they don't like that when I turned it in. It's like, that's the way I write. So people have their own styles, but hope this is okay with you guys. So if x equals 0, y equals 0 also. So the only solution to the initial value problem, that's what IVP stands for, that works is going to be y at 0 equals 0. So this does not have a unique solution if I took y at 0 to be anything else. So really when I say there's a unique solution that exists, I mean that for any given initial condition, there's a trajectory I can run through it. That was true for the weight loss model. I knew that ahead of time when I gave you that problem. I knew that that weight loss model that I developed is going to work for any initial conditions. But it would be terrible if Theo went back to his room and found out he worked his initial condition and there wasn't a solution for his initial condition. So this is actually really important. And it's in all my applied math differential equation papers, I have an existence and uniqueness theorem that's attached to it, and sometimes non-negativity. Any questions? Lovely having this first thing in the morning, right? It could be real analysis, it could be worse. And by the way, if you have y at 0 equals 0, you don't have unique solutions either. Blew it every which way. Such an innocent looking thing. You guys have that project at the end of Jedi Math where some people actually develop, do they talk about this? That your solutions might be negative. I think that might be out of the scope of the class, but it could easily happen. You know, that project that you have where you have like posters up on the. So the only time it has a solution is this, and I didn't write this in the notes, and it's not even unique. So it's not good. Think of it as this way. If you're trying to model something, like say it is weight loss, that was the first example that we had, then you don't want there to be millions of solutions for your initial condition. Which one would you pick? So bad. So that means also, like, if I put y at 0 equals 1, it doesn't have a solution. So when I write something down, I'd like, one of my friends calls it checkability conditions, some conditions on the function f, the right-hand side, to guarantee that I have a solution. And by the way, these symbols here, this means an element of, this is the notation for the real numbers. I took a lot of undergrad differential equations. When I got to grad school, you realize all these small things that you really don't worry about as an undergrad are super important. This tells you where your phase space lives. So this is a one-dimensional model because it has one initial condition, and the place it lives is in the real numbers. You can ask yourself, where else would it live? Yeah, you can write down differential equations where things can live in very weird places. The book has several theorems. This is out of section 2.5 and 2.8. I find them highly dissatisfying, though. It's almost like they said, let's do this with these guys, and then they're backpedaling off and saying, okay, maybe this is a little bit hard. But I'm going to go through it the way I want to, and I'm not going to do the successive approximations they have in the book. If you want to look at that, it's fine. That's how they write the proof for their theorems. I'm not going to prove the theorem. I'm actually going to make it useful. Like, this is how you use it. That's more important. Existence and uniqueness theorem is theorem 2.4.2, so it's not 2.5, 2.4. And it's for first order nonlinear equations. And I find that dissatisfying because you're going to quickly move to second order and then higher order equations, and then you have to have new theorems for each thing. So that's just like, I just want one checkability thing that works for everything and not have to relearn something when you change dimensions. But here's how I'm going to explain it with an example in the middle. When we read pure mathematics, and you probably never had to do it in the past, nobody made you, unless you had a weird teacher, which you don't usually at West Point have weird teachers like that, but if you go to civilian colleges, you do. Somebody might teach Hilbert spaces in Calc 2. They do weird things. And you might have had a high school teacher that made you do proofs in a Calc class. I did. I had somebody that did that. So they'll work you through the notation. So whenever I read something like this, that looks like blah, 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 I start to like want an example. I don't finish the theorem writing it down until I see an example. So I had to like make an example for myself. So I made an f of t comma y for myself just to see what's going on. And then I took the partial derivative with respect to y, which is what it said to do there. It said, here's an example of an f. Here's an example of taking the partial derivative with respect to y. And this is continuous for y's that belong to r. So I got a picture in my head of this gibberish that came out from the math book. I call it reading with your pencil. And it's very weird and different than what you probably have done in the past. And I don't have a T0, Y0. I just saw that it was, I just have an example in my head to start off with. But T0, Y0 probably is an initial condition. That's my guess. So this is actually the checkability condition. I don't have it written down for some reason. I don't know if somebody interrupted me at home when I was writing my notes, but if this is continuous in some kind of rectangle, and it doesn't have to be a rectangle, it could just be something like it could be a weird looking smooth space, like a circle. It could be a circle. So it doesn't have to be, this has to be a bounded set. If it's continuous over that bounded set, you have unique, your solution exists and is unique. So that's the checkability. You basically take a partial derivative, and you show that it's continuous. I have to make sure that I don't give you real analysis and consequence. Pretty close though. It's a busy week. Yeah, the printer by Father Costa's office has color, so. Last but not least, right? If you look at this, the formal definition of absolute value as a function is a piecewise defined function. It's going to be y if y is bigger than 0 and negative y if y is less than 0. So you have to work out both case. You can actually say, okay, I don't really care if it's continuous. So if I have y, how did I write this? Y prime is equal to ty. It looks innocent, like the other equation. This is just going to be and minus ty if y is less than 0. And I guess 0 if y is equal to 0. You already can see probably a problem with 0. So work it out. This should be easy. Put your work on the boards so you're moving around and not falling asleep.